Hello, my name is Florent Duchesne. I'm a researcher at SARFAX, which is a research center in Toulouse, in France. And today I will give you some results we obtained on COVID propagation. And the title of my talk is High Performance Computational Fluid Dynamics for Virus Propagation in Closed Ventilated Spaces. The computation have been made thanks to an allocation provided by PRACE in Europe, as well as by Agency in France. So the main topic of this work belongs to virus propagation. Here we talk about COVID and SARS-CoV-2 propagation, but it can relate to a lot of type of viruses. And we know today that there is some routes of propagation. And the one we will talk about here is airborne propagation. So there are, with this type of propagation, different type of routes. The first one being when two people are very close together, and this is why there are advisement to be far from other people. And this route is the most dangerous, and this is why, for example, we are advised to wear masks. And there are more long distance routes against which it is very difficult to fight. And this is the one we want to study here, the longest routes that can take hours to propagate. And this is a difficult topic to study because we don't know in enclosed spaces where the respiratory droplets can migrate. So to study this, we will use computational fluid dynamics. And also an important topic is we don't really know how many times the virus can stay active in this environment. And this is why we have to work with biologists in order to, depending on the conditions in terms of temperature, humidity, UV radiation by the sun, for example, on which time or which duration viruses can stay active. So this is a kind of joint work, but today we'll only talk about migration, so about computational fluid dynamics. So when we started this project like 1 year ago today, we checked if our CFD solver was able to simulate airborne propagation, and to do so, we started to study a very close type of propagation, like in between these two people. One is sneezing or coughing here, and you see droplets, very, very small droplets here that are emitted and can propagate at 1.5 meter distance here. So this is based on a short time simulation of about 1 second in this example. But the main question here is now what happens in an enclosed space that can be ventilated, such as rooms, bus, airplanes, cars, theaters, cinema, restaurants, and so on, and what happens on long times. And to do so this is an example of a room that has been provided by GE Smart Building in France. And we have computed the airflow in this environment, which is driven by a ventilation mechanism at the left of the rooms, but also by buoyancy by these two people who are working very hard in this office. And we've made two types of computation just to illustrate the behavior of the droplets in this environment. On the left, you've got a propagation which is just linked to the weight of the particles. So big droplet will fall very fast and small droplet will have a less ballistic trajectory, but you see that almost the table is full of droplets. But when you account for the dynamic of the airflow on the left, you see that very rapidly the whole room is fed up small droplets with airborne droplets here. So taking into account the real configuration, real ventilation, buoyancy, and all the effects that are linked to computational fluid dynamics, to fluid dynamics, is of real importance here. And to do so, we use our solver, which is called AVBP. And this solver is based on a long story we have with Safran, who design aircraft engines. So totally different from what we are looking at here. But this solver solves the Navier-Stokes equation, so what is needed to study fluid dynamics. And also we inject fuel in this system that will burn, and the same type of approach can be used to follow respiratory droplets. So we use Lagrangian formalisms to follow these droplets. So in order to accelerate the computation, we follow a two-step type of approach, which is described here on the bottom right of this slide. First, we use large simulation on the flow field time scale in order to compute the flow field inside the configurations, enclosed configurations, like the room I just showed you before. And then once we've got statistics on this time scale, which are very short, in fact, as compared to droplet dispersion time scale, we compute the droplet dispersion in the enclosed space based on the statistical field that have been obtained previously. And we can compute this on very long time, as Lagrangian solver is very cheap as compared to a large simulation solver. So a two-step approach. And for the first one, we have to use very large computer because we compute like several seconds until minutes of physical times on very big meshes to compute the flow in these rooms or buses and so on. So to illustrate what have been done on a configuration, this is a bus provided by Valeo. Valeo is an industry in France. And we use here the state-of-the-art of our solver, meaning a high-order numerical scheme named TTGC. We use 40 million cells, tetrahedral cells, to mesh the entire bus. And we will use advanced SDS model like WEL model here. So on the bus, there are several inlets and outlets that correspond to ventilation, to air conditioning. And we will see the effects of air conditioning on these systems. So you see that in this bus too, there are several passengers and a driver, and we will see how, depending on the position of the emitter of a respiratory droplet, so droplets will migrate inside the bus. Another thing is that the top air conditioning system will be considered as a perfect filter, let's say equipped with a UV disinfection system, while the front ventilation will be a standard front ventilation. And there is only one outlet in this system, which is at the rear of the bus. Well, the outlet is divided in two types of outlet, but this is only one outlet at the exit of the bus. So this is the type of air conditioning system equipped with a UV system, as you can see on the top right here. Before entering the AC system, normally Valeo provides some system that acts, that embed UV disinfection system. Here we will just consider that this UV disinfection system is embedded in the AC system directly. This is an approximation. And we will consider two operating points. On the first operating point, on the top, all the two air conditioning systems are activated, mainly the front one with the two jets that you can see in the picture, as well as the main cabin AC system that is illustrated by the flow that you can see flowing along the windows of the bus. And this is the system that is equipped with the UV disinfection system. When going to operating point 2, we switch off the main AC system, so we don't see anymore the flow rate along the windows, and we only see the two jets along the driver. So we will see how this two operating condition can impact first the flow field in the bus, and then how it impacts the distribution of droplets depending on the passenger emitter location. So first, let's have a look to the instantaneous distribution of velocity inside the bus. So on the top here, you've got the operating point 1, meaning that the air conditioning system of the cabin is active, while at the bottom, you've got the operating point 2, where the AC system of the cabin is switched off. So we have here a representation of the instantaneous velocity. And be careful, because for the two animation, the scale of the velocity is not the same. On the top, you've got velocities that are more important than at the bottom. This is simply due to the fact that the air conditioning system in the cabin provide a very high velocity ratio here. So we see also a lot of turbulence that is generated by the AC system, which will be very important for the droplet dispersion compared to when the AC system is switched off. So we see very different flow field, instantaneous flow field. So let's have a look to the mean flow fields. Just before this, I want to show you a time history of convergence of this computation. So you've got here the function of time and the abscissa, the evolution of the kinetic energy for the two computations. So when the AC system is on operating point 1, you've got higher kinetic energy, which is due to the fact that you have more air movement in this bus. And when it is switched off, of course, you've got less kinetic energy. So you see that the computation converged very fast to the final state in terms of kinetic energy. 15 seconds for operating point 1 and 40 seconds for operating point 2. And the time average have been made, the time average solution that I will show you after, and on which the Lagrangian droplet dispersion is based on, have been made on a simulation of more than 2 minutes. Okay, so here are the mean view of the flow field inside the bus. So on the top, you've got the operating point named 1 with the AC system that is on. And on the bottom, you've got the operating point 2 with the AC system which is switched off. And you've got the front of the bus at the right and the rear of the bus at the left. You've got rectangles in red and dash red here that represent the outlets of the AC system. Okay, the extraction of air of the AC system to illustrate you a main driver of the flow. So you see that the flow topology that are represented here by streamline based on the mean flow field are totally different in these two configurations. And I will try to just illustrate you in a few words how they are different. You see very strong vortices on the operating point 1 that separates both sides of the bus. Okay, you've got very strong circulation due to the fact that the fresh air coming from the air conditioning flows from top to bottom along the windows, then goes back in the center and goes back to the AC outlets. There is also some kind of separation between the front of the bus and the rear of the bus due to the fact that this AC outlets suck air and separate a bit the rear and the front. When it comes to the operating point 2, the situation is very different. The main driver of the flow are the jets, the two main jets that we can see on the right. And you see that there is a jet that is stopped by some wall just behind the driver, and the other jet can go a little bit further in the cabin and creates a very large circulation zone flowing from the front of the bus to the rear, and at some point coming back, and that creates a small, very slow recirculation zone, but still a recirculation zone in the bus. And what you can see that the passenger at the rear, so at the left bottom part of the bus is not in this recirculation zone here, meaning that is a bit separated from the main flow field in the bus, as well as what happened on the right side of the windows. So this will have a very important impact, all these flow fields, on what will happen when it goes to turbulent droplet dispersion in this bus. So to study this for both operating conditions, we will say that 3 passengers expel respiratory droplets, and we will study step by step. So we'll do a total of 6 simulations based on the 2 flow fields I presented to you. And while the droplet distribution in terms of diameter is presented on the right bottom of the slide, just to illustrate that it follows a law that belongs to bibliography, and there is a lot of a big peak of small droplets and a smaller one for bigger droplets, which is a kind of distribution that we can have when someone is breathing or coughing, for example. So here is 2 animation just for one position, which is in the passenger in the middle of the bus. This passenger is located not far from the AC exit of when in operating 1 it is activated. So if we first concentrate on the operating point 1 when the AC is on, what we see that, well, this is a representation of the droplets in the bus. And the color are, when it is red, the droplets are big, which is why we see red particles on the floor because they just fall at some point, and green particles are smaller. And what you see is that a lot of green particles are rapidly evacuated by the system, are filtrated by the system, or disinfected by the perfect system just designed for the simulation. And you've got some dispersion in the front part of the bus, but not in the rear part of the bus, which is directly linked to the aerodynamic described before. The AC system here very well separate in terms of flow dynamics, the rear and the front of the bus. The situation is totally different when it comes to the operating point 2. You see, once again, red droplets that are on the floor of the bus due to the fact that they are heavy and they fall very rapidly. And while the simulation restarts here, so you see the dispersion, the droplets that are catched by the main recirculation zone and spread all over the bus. And eventually there are some of them that are evacuated by the rear of the bus. Of course, there is gravity here. And if the flow field don't bring these small droplets close to the exit that are close to the floor, they won't go there because they are very light. They are aerosols, so they won't exist or very slightly exit the bus by this exit, in fact. So this is a view of statistics for these 6 computations. And what we see here on this graph on the right is a time evolution during 1 hour, because the simulation has been performed during 1 hour of physical time, of the number of droplets in the system. The first observation that we can make is that in 1 hour, there is no equilibrium between expel, the fact that someone is breathing and generating respiratory droplets, and the outlet of these droplets, either by the perfect AC system disinfection or by the rear outlets. Okay, none of these curves are form a plateau at some point, and they are still increasing and increasing. And the slope of the increase is different, and this is what is of interest here. Dealing with the first operating point, which are the 3 curves that are with fewer number of droplets here, we see that the system, the AC system, is very efficient to catch these droplets and to treat them. While when they have to go to the rear outlet with operating point 2, this is far less efficient in terms of evacuation. There is only when the passenger is close to the rear outlet, so the back passenger in green, that we see an effect of on the number of droplets in time. And what is important to underline here is that we've seen the number of droplets as a function of time. And now I just present you on the right here a plot that illustrates the time evolution of the liquid in the domain. So as I mentioned, droplet can be either big or small. There is a continuous range of diameter between big and small. And what we see is that, in fact, there are mainly smallest droplets that are evacuated either by the rear outlets or by the AC system, the perfect AC system. And this is well illustrated here by the green curve that shows, in the case of the back passenger on operating point 2, that a lot of droplets are evacuated, but this is the point where there is more mass enclosed in the system of droplets. And this means that, of course, the mass of droplets means variant at some point, but while the biggest droplets are less efficient to move in the bus linked to the AC or ventilations. But still, there is a lot of mass that is enclosed, and the smaller droplets are evacuated more rapidly than the biggest one. And well, just to illustrate all the operating point here and the location. So on the left, you've got results from operating point 1, and the right operating point 2. And you've got the location of every passenger for the simulation. So at the top, you've got the middle passenger, and the middle, you've got the driver, and at the bottom, you've got the rear passenger. What we see is that globally, when the AC system is on, once again, you've got no much spread of droplets everywhere in the bus, except when the passenger is at the rear of the bus. If you look at on the left and down of this picture, where you see some droplets going up in the front of the bus in this rear emitter. And when it comes to when the AC system is off, the main AC system is off, when the passenger is located, either the emitter is located either at the center of the bus or at the front of the bus, you see turbulent droplet dispersion everywhere in the bus, while when it is located at the rear of the bus, the main convection pattern do not interact much with him. You see that there is a line of very big droplets that are convected in the front of the bus. And you see that the small droplets just fall very slowly around him and are eventually evacuated. So just finally, to illustrate the kind of physics that we can extract from this type of computation, this is a scatter plot, a PDF scatter plot. In abscissa, you've got the droplet lifetime, and in the ordinate here, you've got the droplet radius, and this is taken at the end of 1 hour of simulation. So you've got, and it is colored by the elevation in the bus, meaning that in red, the droplets are on the top of the bus, and in blue, the droplets are on the floor on the bus. And what you see is that big droplets are on the floor of the bus, and smaller droplets are almost everywhere, but not on the floor, and can flow thanks to the flow field here. So I will show this type of graph for the 6 simulation on the next slide. Okay, so you've got on the top operating point 1 and on the bottom operating point 2. And what we see once again is that mainly smaller droplets are evacuated, when the AC system is on, we very well see it mainly for the back passenger, for which after 1 hour there is almost no small droplets and a lot of big droplets that are convected everywhere. This is seen on the plot on the top right of this slide. And when it comes to operating point 2, you see that the PDF are very filled. You see droplets everywhere in these PDFs and at every elevation. And this was well observed when just looking at the images. So this is another way to look at this type of results. And just to finish the presentation, next. So thanks to high fidelity computational fluid dynamics, mainly large eddy simulation, we have been able to compute several types of configuration, an office and a bus, but we will continue with different kind of scenarios and geometries. And depending on operating point, we are able to simulate the flow field to see the differences and at some point anticipate what can be the turbulent droplet dispersion. And then we are able to very rapidly, thanks to Lagrangian simulation, to simulate turbulent droplet dispersion that can be of very helpful for a designer, like for bus, what type of system and where to implement a system in order to avoid turbulent droplet dispersion, respiratory droplet dispersion. And just to give you a view of the CPU hours that we consume for this type of configuration. So for the bus configuration, you see that it requires 500,000 to compute more than 2 minutes of CPU time on this configuration. And doing 1 hour of droplet simulation, this is only 2,000 CPU hours. So that there is a very important acceleration by doing the two-step approach we've developed. So first, large simulation of the flow field, and then turbulent droplet dispersion to just follow the particles. So all I have presented to you was with strong assumption. For example, there were not viruses carried out on the droplets. There was not evaporation, and all of this is currently studied. So in order to better predict what can happen, and depending, of course, on temperature, because the situation is very different when it is winter or summer in a bus in terms of ventilation, temperature, and so on. And we work with biologists in order to study the virus loading and lifetime, as well as on disinfection purpose. And of course, to propose a mitigation solution modeling to embed in the simulations. So I come to my very last slide. So a question here is how important has HPC, high performance computing, been for this research? Without any access to high performance computer, we wouldn't have been able to provide the LES results of such complex geometry. So I just illustrate here by two types of geometries. And thanks to this, we have been able to produce high fidelity results on big meshes rapidly for different operating points. And without this CPU hours, of course, it would have been taken more than the several months it took us to do so. And of course, we investigated a lot of parametric sensitivities on this simulation. I just shown you today just a very small piece of all the information we have due to a question of time, of course. But once again, without price and jersey on this adventure, we wouldn't have been able to produce this type of results as fast as we've done it. So thanks for your attention. You've got my email contact here and my web page here for more information.